Notice that before that line, EBP var 8 is used for the first time without even being initialized. And it's loaded in ECX. So that's a clue. There's a clue that this is a possible constructor. And notice that at the end of the block where the if statement would end, you'll notice there's a call to another function using the same this pointer, the same value in ECX with the one declared in the constructor. And this indicates that this is the destructor because it's the last one called at the end of the scope. Now, dynamically allocated objects, on the other hand, are allocated in the heap and they are created by the operator new. The operator new has a parameter is passed the size of the object as parameter. So that's another clue that we can use later on to give us a clue on how the objects are laid out. The object size is very important. And the returned value by new is used as the dispointer for the constructor. The destructor, on the other hand, is called via operator delete. This has to be explicitly called, so it can be called anywhere. There are, but it's not always true because there are some mechanism actually in C++ where you can declare the dynamically allocated object that will be automatically destroyed using the auto-PR keywords. Here's an example of a dynamically allocated object. As you can see, the first red line is a call to operator new. And the size, the parameter pass is 4, so the size of the object is 4 bytes. Further down on the second red line, you can see the call using the return value operator new as a dispointer. So that is a clue, that is a possible constructor. And on the third red line, actually also uses the same this pointer, but you actually will not know exact 100% if this is a destructor or not. But you can see that below that there's a free call, so you can see that the object is being deallocated at the point. So that's another clue. And you can possibly say that that function is a destructor. Okay.
So another method for identifying classes is via the RTTI. So it is used for identification of object type on runtime. It is generated for polymorphic classes or classes with virtual functions. Basically, RTTI is used by the operators type ID and dynamic cast. RTTI will give us information on class name and class hierarchy, so it has pretty good information that will give us a rough idea of what the class is. So it consists of several data structures. So the first data structure for RTTI is what we call a RTTI complete object locator. It has a pointer to another two data structure. The first data structure is called the type descriptor. It will contain information about the class, like the class name. And the second structure is the RTTI class hierarchy descriptor. It will contain the hierarchy of the class. So finding the RTTI involves finding a VF table. So you will see when you load a sample in NIDA, you will see several pointers throughout the code. And if you look one D word before, if you see a pointer to what looks like a data structure, then probably it is an RTTI complete object locator. So this is the data structure of the RTTI complete object locator. At offset C, it contains the the type descriptor, which contains the information about the class, and the offset hex 10 will contain the class hierarchy information. So that is what it looks like in this assembly. So put in mind that this one is already pre-processed, so we already modified the variable names. So the type descriptor basically contains the important class name. So if the class of RTTI and then the class name exactly describe what the class for, then you will have a rough idea what the class is for. For in this example, if the type descriptor says the class name is C packet parser, so it probably means that the class is a packet for a packet parsing. So the class name is mangled. It has the class name is in between a dot and then a question mark and then AV, and then the class name and then two at sign. So this is how the class hierarchy descriptor looks like. So the attributes field contains information if it's multiple inheritance or virtual inheritance. So it contains the number of base classes, how many base classes the class has, and then it contains an array of data structure for each base class called the base class array. So this is an example. The number of base classes here is 3. In this example, class G is inheriting from class A and class E. So the number of base classes here is 3, including itself. So you just decrement by 1. And then the P base class array points to an array of RTTI base class descriptor, which will be discussed later. So this is the base class descriptor. So each base class descriptor, each base class descriptor will contain a type descriptor for that base class, and then it contains the VF table offset. It will also contain the VB table, which we'll discuss on the next slide. So the VB table is used for multiple virtual inheritance, in which you will need to up class to a specific class. So in this example, class G is inheriting from class A and class E. So what is the mechanism for C++ to specifically type class to specifically up class to class A and class E? So what is used the class base class descriptor has this pdisp field, which contains the offset of the v table. So it points to 4, which is that 4, and then the VB pointer points to the VB table. So that is the VB table. And if you look at the vdisp field, it contains 8, which means that it points to the third D word inside the VB table. So you would just need to add 16 and the offset of the VB table. So you will have 20. So that 20 is the actual offset of class E inside class G. So this is what it looked like in a graphical view. So there are the classes and then the VF table. So before the VF table, which a pointer to the complete object locator. The complete object locator will then point to the type descriptors. And then the complete object locator also points to the class hierarchy descriptor, which will then point to a base class descriptors, which will then point to the type descriptor of each base class.
Okay. Now that we have identified the classes, it's time to identify the relationships between them. To do that, one thing we could do is to analyze the constructor for each class. Constructors contain very important information, such as the base classes, because the constructor will implicitly call the constructors for their base classes. It is responsible for initializing its base classes. Another important information is the location of the virtual function table. The constructor is also responsible for initializing. Remember that class instance layout earlier, there's the virtual function table pointer field. The constructor is responsible for loading the address of the virtual function table in that field. So you can actually get that information from the constructor. And another thing is that member variables are almost always initialized inside the constructor because that's the purpose of the constructor. You initialize the object. So normally if you program C++, you do most of your member initializations inside the constructor. So you can get most of the info about the member variables inside the constructor. Okay. So how do you identify classes that inherits from another class or single inheritance? You can do that by looking for a call to a constructor that uses the same this pointer that was passed into that constructor. We already know that this function is a constructor. But inside the constructor, there's a call to a function using the same this pointer that was passed to the current constructor. This could possibly be a constructor for a base class. However, we have a little problem here. It looks exactly the same as when you call a member function of this class. So how do we distinguish whether this is a call to a base constructor for a base class or simply a call to one of its member function? Actually, there's no sure way to know that other than looking at the function, the called function itself, and see if it is instantiated somewhere as a class of its own, or see if it's used somewhere else as a base class using the next example in here. Multiple inheritance actually is much easier to identify or much accurately identified because the first base class is the same. It looks the same with the previous example in the single inheritance example. You can't identify really if it is a base class constructor or a call to a member function. However, the second base class is different. Actually, this pointer is changed to point to remember the class instance layout where the class instance data for that base class starts. That is actually used as this pointer in this case.